term is equal to probability that E is 0, h of x given y, and E equals 0, plus the probability that E is 1, h of x given y, and E is 1. Okay, if E equals 0, if E equals 0, we know that no error has occurred. So therefore, if this is true, we know that x equals x hat. Furthermore, because we know y, we know x hat, which is g of x, g of y. So therefore, what's the uncertainty, what's the entropy given y and E equals 0? So in other words, if the error is 0, we know for sure that x is equal to x hat, and we also know x hat. So therefore, x is deterministic given y and E equals 0. So therefore, this term is 0. Now, this term, so basically the intuition there is, if I know that no error has occurred, and I know y, so a Gini tells you no error has occurred, and normally you know y, then you apply y to your decoding function and get x hat, and the Gini has already told you no error has occurred, so therefore you are certain of the value of x, so there's no more randomness in it, so therefore the entropy is 0. The alternative side of that is the Gini for sure tells you that there is an error. So now all that you know is that x is not equal to x hat. Given that x is in the set Sx, how many alternatives are there other than x hat? So we know the only thing that this is telling us now is that x is not equal to x hat.
So cardinality of Sx is minus 1.
Cardinality of Sx minus 1. So what that means number of possibilities for x is equal to cardinality of Sx minus 1. Now, if I know that, so the details that this conditioning is telling me is that the number of possibilities for x, cardinality of Sx minus 1. What is the maximum possible entropy if I have a random variable that can take this many values? Maximum possible entropy is if they're all equiprobable, in which case what is the entropy? Just log of this. So h of x given E and y is equal to this term, which is 0, plus probability that E equals 1 times h of x given y and E equals 1, which is less than or equal to probability that E equals 1 times log cardinality Sx minus 1. So if all of these guys are equiprobable, then we have that the probability is 1 over that, and then the entropy is the average of the log of the probability, but all the probabilities are the same. So log of 1 over the probability is just log Sx minus 1. So what do we have left? We have h of x given y. We already had the first term, which was h of e given y, which is less than h of e, excuse me, little h, sorry, h of e plus the probability that e equals 1 times therefore an error has occurred. What's the probability of error? The symbol I used. It's PE. In this specific instance, I define it as PE. So E is 1 with probability PE, so therefore E is 0 with what probability? 1 minus PE. So therefore this, because E is binary, this is the binary entropy function with probability PE plus PE log cardinality Sx minus 1. And that's it. Now, we can weaken this bound. We can weaken and simplify this bound. We know that H of PE, the binary entropy function, is always less than or equal to 1. So therefore, we can also say less than or equal to 1 plus PE log cardinality Sx minus 1. What's more, well, actually, never mind, that's not really important.